Welcome to the launch event of the Technology Access Program for Digital Security by Design. My name is Dana Elman, and I'm an innovation partner and the program lead for the TAP program at Digital Security by Design at Digital Catapult. Today is a great milestone. As we extend an invitation to businesses and industry to get involved with Digital Security by Design Technology Access Program. Digital Catapult is the UK authority on advanced digital technology. We bring together experts from the community of researchers, startups, scale-ups, and industry leaders to discover new ways to solve big challenges for unlocking the UK's future potential. We have a neutral position in the market. As you can see, we work with various types of organizations, from government, public sector, to startups, investors, corporates, and the Catapult network. Digital Catapult is part of the Catapult network that supports businesses in transforming great ideas into valuable products and services. And now I'd like to present the agenda we have for today. First, we'll hear a welcome and introduction to Digital Security by Design from Professor John Goodacre, Digital Security by Design Challenge Director at UK Research and Innovation. We'll then hear a presentation on common vulnerabilities in modern computer systems from Matt Evans, Computer Architecture and Security Advisor for Digital Catapult. After then, we will continue with two presentations introducing Cherry and Morello from Professor Robert Watson, Professor in Systems Security and Architecture at the University of Cambridge Computer Laboratory, and from Richard Grithwaite, Chief Architect and Fellow at ARM. We'll then have Q&A facilitated by George Papadakis, Senior Innovation Lead for Digital Security by Design at UK Research and Innovation. After these presentations, we will hear from a panel chaired by George Papadakis, inviting Professor John Goodacre, Richard Grithwaite, Paul Waller, Head of Research at National Cybersecurity Center, and Professor Madeleine Carr, Professor of Global Politics and Cybersecurity at UCL. After the panel and Q&A, we will have a final presentation on getting involved in the Digital Security by Design Technology Access Program with Katie Ho, our Head of Innovation at Digital Catapult. I now would like to invite the first speaker, Professor John Goodacre, Challenge Director for Digital Security by Design at UK Research and Innovation.
Thank you and welcome. So what I'm going to do here is basically introduce the technologies, or the program itself as opposed to the technologies. But first, let's look at really, the world that we all live in. So clearly over the years, digital technologies have been becoming more and more ubiquitous in society, both in terms of things we hold and use, in terms of the mobiles, the things we see, but also lots of devices that we don't see. So all the ones that are running the critical infrastructures, the clouds, and the things like that. So really, you can ask yourself the question, is it a case that actually we're heading towards a cyber disaster? Because if you think about where we're coming from, we've had sort of the fairly popular desktops and servers running a limited number of operating systems. They've really matured what the mechanisms and the approach they take to maintaining patches, keeping things secure. But in this world of diversity, we're also diversifying the number of vendors, the different locations, the different places that will actually be delivering these. And clearly, not everybody is the size of a Microsoft in terms of being able to handle patch distribution and things. So really, it's a bit of a problem on its way. So cybersecurity today, really, you can look at various aspects of it. You can look at really, it's focused on the mitigations of keeping up with those patches. And unfortunately, the primary responsibility is pretty much falling on the users of that software. So it's the point of use. It's, the security comes in at the point of use of those systems. And it's very disruptive, costly, and really, there's no defense against a flaw in the system. So the idea that the system is perfect and obviously you just make sure that only the right people get access isn't, unfortunately, the world we live in. That's really come to a head because technology is being developed during a period where the performance and cost are more important than cybersecurity. So, it's obviously not the case now because there's a hugely increasing need for businesses to really start asking the questions, is what I'm getting delivered being designed with security in mind? is it a default configuration that I get which is secure, or do I have to go through a long set of configurations to actually secure that product? And then really those vendors that are then building those products start asking themselves the questions, is the technology I'm using itself secure? Can it provide features by their actual design in which they can protect? So please start thinking about those sort of questions when selecting and deploying new software solutions. And really, that comes to a head when you start seeing what the point of view cybersecurity tools of today promise. You know, they say how to prevent security vulnerabilities. Obviously, I've tried to hide the actual company here, but it's not unusual to actually see go around a cybersecurity event, everybody saying, buy this tool and you will be secure. We can prevent those vulnerabilities. Well, vulnerabilities are like mistakes, whether or not they are configuration and human mistakes or the mistakes in the way that software is written. So lots of questions that you should be asking when people claim that they're going to make you secure with their latest monitoring tool. So why does DSDB as a program exist? Well, really, we can go back to about 2018 when the UKRI, the Research and Innovation Agency, the government asked basically industry, what's your challenge that the Industrial Strategy Challenge Fund could help solve? And that's really where ARM and other partners got together and said, look, actually, there's a failure in the market. What this basically means is that hardware vendors can't change things that make software not compatible anymore. So yes, they can add features, they can create new capabilities within the processor, but to fundamentally change something in the middle, basically wasn't able to just simply flow through the business as usual supply chain. And that took the attention of the UK government, and by 2019, there was a program that was announced called Digital Security by Design. And really the vision for digital security by design is all about overcoming those market failures and radically update the foundation at the center of those digital computing infrastructures. So in other words, it's the first time that really that we're aware of that a program has started right at the beginning of something that hasn't really changed for multiple decades. You know, the people were seeing problems back in the 70s with the way that computers had been discovered, if you like, or invented, I suppose, a better word. So what we did was create a delivery plan for this. We split it up across what we call the enabling technology, the actual introduction. That's where we'll be hearing from Robert and Richard in terms of what the technology looks like. We'll then have the technology sector itself, those that are actually going to be building the products and services, and obviously the technology access program that we're going to be talking about again today lives there. But a further part of the program has actually been working with the industrial sector, if you like, the end users, for them to sort of look at how that technology can impact the way that they do business and bring better secure products to their end customers. So the biggest part of this, and again, Richard will be talking about the Morello program in much more detail, was the creation of a hardware prototype that could actually be used to research and understand the impact and the cost and the benefits of introducing this fundamental research change. If we're making such a fundamental change, however, there's a lot of questions that come up. There's the questions that go right to the root of software design. There's questions in software verification, historical decisions in how virtual machines work, how the cloud works. You know, basically, we gave the academic community in the UK an opportunity to go and actually say, okay, you can have early access to this, see what shakes out in terms of any fundamental changes and enablement. We'll hear obviously more about the technology access program for the technology inventor sectors, in addition to what the research community have been doing. The other part of cybersecurity is obviously the social aspects. We can't ignore that technology doesn't just exist. Okay, it exists in an ecosystem. It exists with adopters and stakeholders that need to select and use it. So actually a major part of our program has been both enabling core research into the social and economic aspects of this change, but also to help support and create a new ecosystem, new network around the people involved in creating and realizing these new technologies. The other half of this, so we've got the hardware platform, we've got the social, the third half, if you like, just to make it really difficult in describing, is the software ecosystem itself. So the idea that we have to progress the fundamental building blocks for software, the operating systems, the libraries, the tools, and there's been a couple of programs here. The first competition we had was for a number of SME companies, basically to give them early access and look at what the technology could do for their businesses. It's gave them that insight, and obviously we've probably got a number of such companies on the webinar today. And then another set that's coming specifically at the enablement, the idea that the tools and the environments, the libraries, the information that's required for the broader adoption of these technologies. Again, a competition which hopefully is starting next quarter has been defined within this part of the program as well. And then the final part has been exposing it to the industry sector. The Hub Group, a major e-commerce company, has been looking at what it means to have secure e-commerce using these technologies. And then we've got 4 new ones that were announced just as part of the government's new national cyber strategy that go through networking infrastructure, automotive sector, critical infrastructure, and the data center. So lots of exciting new places that will become interesting to be first adopters of what something that is expected to become ubiquitous across the whole digital ecosystem. So where next? What's next? So obviously we need to extend this discussion. Cybersecurity for decades has been speaking about the best practices, the patch profiles, how often you need to maintain them, the severity of them, the logging of them, but really in essence has done little to stop them and block them. So we need to start looking at how the earlier parts of the value chain, both in terms of manufacturing, can design systems in a way that are more secure by default, but also the technology providers in the way that they can provide technologies which have features which, if you like, by design provide improved security capabilities. So really that's where we're at. We're starting opening up the visibility of really what could be quite a large step change in what people expect of computers and the trust that they will be able to place in such systems. So I believe what we're going to do next in the agenda is Matt's going to talk a bit more about the world in which we live in, so that we can then understand obviously how the technologies that will be introduced later come to that, and then obviously where we go in the future in terms of providing access to these technology companies to understand these new techniques and how they can overcome any commercial or performance barriers that they may have in understanding how they can adopt security, improve security in their products. Thank you very much.
Thank you very much, Professor Goodacre. Now I'd like to introduce Matt Evans, Computer Architecture and Security Advisor at Digital Catapult.
Thanks, Anna. Good morning, everyone. Okay, I'm going to give you a short introduction to common vulnerabilities in modern computer systems. So it's 2022. We're surely experts now at building computers, writing software. We've been doing it for quite a while. Why do vulnerabilities still exist? Why do we still have them? Well, the short answer is computer software, computer hardware and software, both extremely complicated. And we are but mere humans writing it. Software is very difficult, and you shouldn't underestimate the power of a simple typo even, or a small error, to have quite catastrophic consequences in some aspects. We need to, as we're building these software projects, put a huge amount of effort into the security analysis. And I think it's fair to say that some projects don't necessarily put as much effort as others into trying to analyze all possible threats and trying to foresee all possible situations where something might go wrong. So as we try and build more and more complicated pieces of software, we try and deal with this complexity by scaling up our teams, by having multiple components, by having multiple teams dealing with those components. And when we've got multiple groups of people, we've always got scope for misunderstandings. And unfortunately, that's also a source of bugs, a source of issues that can lead to security problems. So perhaps design parameters or assumptions are broken when a module from one team is used in a different way. perhaps just a global misunderstanding of what some of the threats might be or how your product might be used in practice. Reusing existing code that might be absolutely perfect might end up causing problems where that code is used out of its original design space, perhaps hitting some of its limitations that weren't really anticipated by its authors. And this has happened quite a lot, where a library, for example, might be used in a new context that wasn't anticipated, and with a new set of threats or information from malicious parties being parsed by an image library springs to mind. Code reuse is a good thing, though. I mean, we can't be writing everything from scratch each time. It's economically not viable, but also, code reuse gets a lot of eyes, particularly with open source code. A lot of eyes on the problem, and it makes code more robust. But we have to be aware of what the limitations are for modules or libraries that we import from elsewhere. But the final, I would say, the villain of the story, I would point towards C and C++ as languages I love, but have many pitfalls. I think we can all agree that they're some very powerful languages that let you do some quite funky things with pointers that are not always a good idea. And it takes a lot of discipline and a lot of care and a lot of effort to write really, really good C and really robust and secure C. So these languages are incredibly popular due to their age and various other, large projects using them. So we're not getting away from these languages anytime soon, but we're not really helping ourselves here. The choice of these tools exacerbates the challenges of complexity and trying to apply security or trying to make our systems secure. We use an enormous iceberg of software that comes from elsewhere. So, we really are standing on the shoulders of giants when writing software these days. Most of that legacy software is C and C++. So looking a little bit more detail about what kinds of things go wrong. This is by no means an exhaustive list of the types of vulnerabilities or reasons they happen, but just to sort of give you a flavor. So for logic problems, perhaps a design choice doesn't age well or doesn't really anticipate some of the problems that may occur. So choice of weak cryptographic algorithms is one example. There are many, many ways for implementation of that design to provide scope for bugs, let's say. Not correctly sanitizing input from the outside world. Numerical problems are rife. That can be very fiddly to prevent overflow or signed and unsignedness issues, making sure all data is initialized correctly and so forth. These sorts of things are particularly problematic when implementing cryptographic algorithms. This needs special care, and this is a good example of why code reuse is a good thing. The rule of thumb tends to be don't implement your own cryptographic stuff. Use a tried and tested library that's really been hardened and had a lot of review and testing. Race conditions are quite an interesting example of where vulnerabilities can come in. So your design might correctly say, okay, well, we have some data from the outside world that's untrusted. Let's validate that data before we consume it. But if the implementation accidentally doesn't prevent that data from changing while we're checking it, then we have a problem. So, for example, an attacker can provide good data, get you to agree to it, and then change the data as it's being consumed, which leads to this time of check to time of use issue. I've saved the best for last. Memory safety issues are the majority of causes for vulnerabilities that are being exploited today. We'll see some statistics in a later presentation, really very interesting. And these are particularly a problem with the languages C and C++, which is why I've called them out particularly. So doing an allocation, so in C you would malloc something, perhaps you do some interesting pointer arithmetic which causes an access off the beginning or off the end of that allocation. Perhaps you free something, yet it's accessed after it's freed. That will then lead to someone else perhaps being able to control your input data. When these sorts of issues occur on the stack, then we've got even more problems. So a buffer overflow on the stack turns an overflow or a data corruption problem into a control flow integrity exploit, potentially. And that can lead an attacker to have quite a wide range of interesting behaviors. And an attacker is able to do a lot of interesting things with control flow exploitation of our software. So there's some problems. What can we do about it? Well, unfortunately, we're not going to get away from good old-fashioned hard work, good engineering. And really, this is our development process is prioritizing security right from the start. So thinking in depth about anticipating problems, testing strategies, making sure that we're actively looking for problems and actively reviewing and keeping coding standards high to try and save us from ourselves in many ways, keep away from particular coding idioms which happen to be known to be problematic. Defense in depth is a really important one. So we have to do all of this hard work to prevent bugs, but anticipate that they will happen and try to layer our software or organize it in a way that will reduce the impact if bugs really are exploited. We heard a little bit before about areas where people are researching into improved verification and tooling. I think this is a major area. I'm very impressed by some of the kind of coding editor assistants these days, which can look at your code as you're writing it and suggest, well, do you really mean this instead, or is this idiom going to cause problems? But I think this is an area where we're going to see a lot of benefit to take a lot of the effort away from, or the complexity away from the humans, and have a lot more automation in the tooling that can help us avoid these bugs. Coming back to memory safety, well, I mentioned that C and C++ are kind of dangerous variables when we're thinking about memory safety. So one way of approaching this is to simply not use them and use memory safe languages, whether that's managed languages like C# or others like Rust, which will perform runtime bounds checking, and they'll prevent you from actually being able to make an out of bounds access. This is very powerful. The problem is we have that big iceberg of all of that legacy code as well. And in many cases, our software, we don't necessarily have the choice to not use C and C++. And wouldn't it be nice if we could bring memory safety to C and C++? Now, I've spoiled my own punchline here. So this is where Cherry is providing advances. So let's give a little overview of Cherry. The later presentations will give detail about how and why Cherry is doing what it does, but it provides two main features. The first, it provides a mechanism that enables us to write memory-safe C and C++ programs using these architectural capabilities that are introduced by Cherry instead of pointers. With some clever compiler technology, this can also benefit existing C and C++ code with a very low-touch improvements to existing programs, which is extremely important to help that big legacy of code that we're building our industry on. So this lets us this provides hardware bounds checking. So it lets the CPU do this bounds checking for us instead of the programmer having to think about it in the case of C and C++, or the runtime having to implement code to do this in the case of managed languages. So there are also opportunities in managed languages. So where you'd have a runtime that might itself be written in C, then there are improvements to its robustness that Cherry can confer there. Or perhaps there are opportunities for the runtimes themselves to use capabilities and perhaps take some of that runtime bounds checking away and do that in hardware instead. The other really interesting feature that Cherry provides is that of fine-grained compartmentalization. This gives us a low overhead isolation of software components, even in the same application process address space. So instead of existing methods where we might, for example, split an application across several processes and use shared memory, it's quite a coarse-grained memory management way of separating data out. This allows us to apply the principle of least privilege in a very fine-grained way to different parts of code running even in the same address space with a very low overhead. And this lets us think about software architecture in a different way. So separating out data that one particular part of the code shouldn't access. It's one of these, the purpose of these compartments is really to assign a footprint of data that the code in that compartment can access by design. And if an external actor finds some way of tricking that code into using a random pointer from somewhere, it's prevented. So the code can only use the footprint that compartment is associated with. And this is a really powerful technique. I think that the scope for thinking about software a different way is going to be very interesting to investigate here. So I'll wrap up here and we'll hear more about how these benefits are realized in Cherry. Thank you.
Thank you very much. I'd like to invite Professor Robert Watson, Professor in System Security and Architecture at University of Cambridge. After Professor Watson's presentation, we will hear from Richard Griffithwaite, Chief Architect and Fellow at ARM.
So I'll talk to you hopefully on the more brief side to give you a bit of background about Cherry, which is the technology underlying Morello's security extensions. So this is extremely collaborative work, as you'll see from our long list of co-authors. I want to particularly acknowledge my co-investigators, Simon Moore, Peter Sewell, and Peter Neumann. So just to briefly introduce, Cherry is a new hardware technology. It's an extension to process designs that is intended to mitigate software security vulnerabilities. Work on Cherry began at the University of Cambridge and SRI International in 2010, supported for about a decade by DARPA. We began a collaboration with ARM in roughly 2014, and supported by UKRI in 2019, ARM announced their Morello processor system on chip and board, which Richard will tell you about in a few moments. What I'd like to do today is talk to you about what Cherry is and a little bit about how it works, what kinds of software we're currently able to run on it. Certainly, we're not yet running all the software we'd like to, and we have high ambitions to run much more. But of course, a point of this research program is to help bring software ecosystems to the Cherry architecture, and then tell you a little bit about the kind of evaluations that have been run to date. And this is important because part of the Technology Access Program is asking for feedback and experimentation with the platform to help us understand how to improve it on the pathway to potential future products. So what is Cherry? Cherry is a processor architectural protection model. You'll notice throughout this talk, I'll use the term architecture. I'll be referring to the instruction set architecture of a processor. It composes an idea, something called a capability system model, with the hardware and software running on the computer system. And what we do is we add new security primitives to that instruction set architecture, new instructions that we can use and new data types. And then this is implemented by the microarchitecture or the hardware inside the processor and the broader chip. And this is going to, with any luck, enable new security behavior in software that runs on top. So what kind of new security behavior do we want? Well, the goal of Cherry, suggested by Matt, is to mitigate vulnerabilities in C and C++ trusted computing bases. These are the critical pieces of system software, language runtimes, hypervisors, web browsers, and so on, that actually are responsible for a vast bulk of the security vulnerabilities and exploitation that take place today. Cherry enables two kinds of new functionality. The first of these is fine-grained memory protection. The goal of this is to deterministically close to the greatest extent possible, vulnerabilities and also exploit techniques that are used and relate to memory safety in C and C++. The second aspect is scalable compartmentalization. This takes the idea of software sandboxing and allows us to substantially extend and enhance the way in which we compartmentalize software by breaking it into pieces that are isolated and protected from one another. What does this look like in the big picture? Well, as I said, we intervene, if you will, in the instruction set architecture, adding these new data types. In the microarchitecture, we implement new features, such as this capability data type. We introduce tagged memory, and these collectively serve to enforce a set of invariants, controlling the manipulation and use of capabilities on which we're going to build other kinds of software data structures and types, such as pointers. There are a set of rules for that use and those manipulation rules like monotonicity, provenance, validity, and so on. They're going to prevent the injection of values and their improper manipulation. To move up the software stack, software is going to configure and use those capabilities. Sometimes this will be done automatically as a result of compilation. Sometimes this will be done explicitly as a result of programmers describing what it is they want to protect and prevent. And we're going to get out of that sort of these low-level memory safety properties, but also higher-level constructs such as compartment isolation. Talk a little bit more about these two properties. So efficient fine-grained memory protection is intended to close vulnerabilities and prevent exploitation. These are similar and yet different concepts. The goal in the Cherry design was strong source code level compatibility. This means that programs have to be recompiled. There is a binary incompatibility that is comparable to the upgrade from 32-bit systems to 64-bit systems. Your 64-bit systems can run 32-bit code, your 32-bit systems can't, and there's an ecosystem update to bring the world towards 64-bit. And you can do an incremental deployment of 64-bit while still running your 32-bit software. Cherry's protection is deterministic and secret-free. These concepts are important. They distinguish the work in Cherry from many other mitigation techniques that exist today as they bring spatial and temporal memory safety. Secret-free is especially important because it's quite hard to keep secrets in the world of computer science. Leaked data values, the ability to attack more probabilistic protection mechanisms really weaken the fundamentals that are intended to protect the software stack from exploitation and arbitrary code execution. Thus far, a number of retrospective studies have looked at the impact of Cherry memory safety with any limitations it comes with, and concluded that they would deterministically close roughly 2/3 of past memory safety vulnerabilities. I'll come back to that point in a few minutes. And that on the whole, in the early studies, the overheads of this are modest in terms of performance overhead, somewhere between 0% and 5% overhead, depending on the type of workload, but that there are workloads which experience higher overheads. And those are workloads we particularly want to explore and optimize as part of the research program. Second aspect, again, was the software compartmentalization. Here, Cherry supports a number of different, what we call software operational models. You can encapsulate objects inside your processes. You can improve the performance of process communication. The goal of software compartmentalization is to increase attacker workload. Attackers have to find and then exploit multiple vulnerabilities. We see this used in sandboxing today. Compartmentalization allows us to take this much further. The attacker workload is increased because in order to fully exploit the system, they have to perform many of these attacks. They have to grow the length of their exploit chain, and that is both a significant investment of work or financial investment. The claims we make today in terms of evaluation are that in early benchmarking on FPGA-based designs, we've seen as much as a 90% reduction in inter-process communication overhead, which means you can afford more compartments than you could afford in earlier designs. There are other things that you can do with Cherry, tend to be on the more researchy side currently, looking at the reinforcement of language runtimes, safe communication between different programming languages. These will also be important things we can do with Cherry, but they're not yet things we're encouraging the non-research community to do. They aren't yet well understood techniques. Probably can't get away without telling you a little bit about capabilities themselves. Capability extends the integer memory address used in the computer system to access memory. It adds additional metadata controlling how it can be used, and it adds tags protecting the integrity and the safe derivation. So when you modify the value of a capability in an improper way as a result of memory corruption or injection of the network, it is no longer possible to dereference the capability as the tag has been cleared. Again, just at a high level sketch, what is the impact on software? Well, your software is, both explicitly and implicitly a web of pointers and interconnections. Integer addresses allow you to access the globals, the heap, the stack, and so on, the memory execute code. Under the hood, they're also protecting implied pointers to implement access to globals or to implement the stack itself. What we're going to do when we use Cherry memory safety is substitute capabilities for integers throughout the compiled and linked code, which is going to reinforce the existing code structure with few, in some cases, if any, modifications at the source code level. The bounds and the permissions associated with the capabilities are going to be refined by various pieces of software in the system, from the kernel and the linker, compiler-generated code, the memory allocator, and so on. Most of these changes will be invisible to most programmers. And then the hardware is going to enforce these rules, requiring memory access to occur through capabilities and not in other ways. And the tags will ensure the integrity and the provenance validity of all pointers implemented in terms of capabilities. These capabilities, as I said, are refined by software, and we have a number of kinds of protections out of them. Referential memory safety is the protection of the pointers themselves from corruption. Spatial memory safety and privilege minimization allows us to restrain pointers so they can only access the intended memory. And temporal memory safety prevents use after free attacks or use after reallocation attacks from allowing confusion between different objects. It's a commonly used attack technique. These are applied automatically, both at the language level, so the kinds of pointers that programmers are working with daily in their data types, and also what we call the sub-language level. You might wonder, if you have strong language level protection, why do you need sub-language protection? Well, the answer is both that there are limitations to what Cherry can do, but also the programming languages themselves require a certain amount of type confusion in their current designs. And so we need to reinforce what falls underneath the programming language in order to protect against openings opened by the structure of the programming language. I won't talk very long about compartmentalization scalability, but I'll explain that Cherry is intended to dramatically improve that scalability. We want to have more compartments. We want to be able to change between them more quickly, and we want to be able to share memory between them much more quickly. And once we have these facilities in the hardware and the software stack, we're able to use them for a variety of purposes. One example might come to mind is if you have a mail reader or a web browser, they are convergence points between data from many different potentially malicious parties. And today we can use processes in computer systems to constrain them to some extent, but the constraints are very coarse-grained. We can isolate an entire tab of the browser or maybe access to a site, but we cannot afford to isolate the processing of every image. If one malicious image comes in via a mailbox, for example, the attacker should not gain access to all the other messages in the same mailbox. And this is the kind of thing we'd like to be able to do by deploying Cherry and using it in our software. Unlike memory protection, there is an implied change to software structure from using compartmentalization. The extent of that change is not well understood today. When we sandbox software today, the changes can be disruptive. They can require structural change, and other times they can flow very naturally. And so this is one of the topics we'd like to explore as part of the Morello research, is the impact on software structure and the potential expense in developing and maintaining those structures. Just talk a little bit about software stack that will be available once you have access to the Morello board. There are in fact two software stacks. There's a software stack developed by the University of Cambridge and SRI, shared components with a software stack provided by ARM. The University of Cambridge and SRI stack is a complete open source software stack, compilers, operating systems, hypervisors, debuggers, and so on to demonstrate Cherry. They're intended to use Cherry extensively, but in an incrementally deployed way. They're intended not to fully and extensively disrupt the software stack. We want to keep around those properties that we like about current software designs. At the bottom of the stack, we have a Clang LLVM-based compiler suite. ARM has extended this to work with the Morello platform and not just with our Cherry research prototypes. Well, we will have, although we haven't yet released, an adaptation of the Google Hafnium hypervisor. We then have a FreeBSD-based operating system stack, Cherry BSD and Morello. This includes memory safety and compartmentalization features throughout its design. Memory safety in all user processes, as in the kernel, different mechanisms for compartmentalization, and also, in fact, as of a few days ago, support for Morello extended Beehive hypervisor, which allows us to host guest operating systems that themselves use capabilities. On top of that is an open source application suite with applications from KDE and WebKit, Python, and so on. This is a growing corpus over time. Its size is limited today, but we've been able to demonstrate rich use up and down the stack. I'll leave it to Richard to discuss the software stack being provided by ARM that includes both Android and Linux adaptations. Talk very briefly about evaluation. One of the most interesting pieces of evaluation work was an independent evaluation performed by Microsoft Security Research Center, MSRC, who are both Microsoft's red team and also help and assist with evaluating new security technologies. The metric that they use to understand the effectiveness of technology is the extent to which it avoids the need for software updates, since software updates incur high risk to customers in terms of impact for potential downtime and so on. They consider a vulnerability to be mitigated if no security update is required. It also, there is considerable engineering and QA effort that goes into the production of updates. It's quite a big deal if you're inside Microsoft, if you can substantially reduce the extent to which vulnerabilities are considered exploitable. They've written up a great blog post and a 42-page technical report looking at these topics in details, which I will leave to the reader. But the key point is that this deterministically mitigated at least 2/3 of those issues. And just a final case study I'll mention briefly. This was an Innovate or UKRI funded study at Capabilities Limited looking at adapting an open source software stack. We selected a significant slice of the software. We implemented memory safety and we whiteboarded compartmentalization. We then evaluated those changes by looking at lines of code modification and a 5-year retrospective vulnerability analysis. The full report is available online. The key outcomes were that we adapted 6 million lines of code in roughly 3 months, compiled for memory safety, did 3 compartmentalization case studies, and overall achieved a 0.026% line of code modification rate across the corpus, and a roughly 74% mitigation rate for all vulnerabilities using memory safety and compartmentalization. I will point you, just to conclude the talk, at our Introduction to Cherry technical report, which discusses the approach to architecture and microarchitecture in some detail. This report slightly predates Morello. We will have a new version of this report out soon that also covers Morello, but the concepts all apply quite well. So in conclusion, Cherry are these architectural primitives requiring some rich hardware and software evaluation. We're able to provide fine-grained memory protection for C and C++, compartmentalization techniques that are significantly higher performance than traditional MMU-based techniques, and also now an experimental implementation from ARM where we can evaluate some of these claims at a much larger scale and explore deployment issues. I'll point you at our website and a number of technical reports there, which will perhaps answer some of your questions and help you explore these topics in more detail. Thank you very much.
So following on from Robert's presentation, I'm now going to talk on behalf of ARM about our involvement in this program, which is under the code name of Morello, which we're making widely available through this technology access program. And I would say on behalf of ARM, we're very excited about this overall program. We want to thank UKRI for its creation of the Digital Security by Design program overall and the opportunities this is giving to explore this exciting technology. So just a reminder of what ARM is. ARM is the owner of the world's most widely deployed CPU architecture. We design process designs that we make available to many silicon partners. Most of the world's major silicon companies produce processors based around our technology. We have about 2,000 active licenses across the industry with 600 licensees, and around 2 billion of our processors have been shipped in a whole range of different markets, from obviously things like mobile phones, where the vast majority of mobile phones run on ARM technology, and also increasingly in things like networking, in servers. The world's largest supercomputer at the moment, Fugaku, is based on ARM technology. But it's not just the big systems, also many sensors and embedded processors in things like automotive systems and so on are based on ARM. We're seeing many billion devices actually being shipped each year now as a result of the wide use of our technology. And we're very excited to explore how to improve security, because security is a fundamental challenge for computing along the lines that Matt talked about. It's not a solved problem by any means. These vulnerabilities, these can come from a simple typo, have they've been around, the concepts have been around forever, and they keep on coming, and the sheer number of things like memory safety issues that exist are a real concern. So with the Morello program, we're really looking to provide a platform to help people explore the Cherry technology that Robert was talking about a few minutes ago. Security vulnerabilities are a huge problem. Cherry has a lot of promise. The studies that Robert talked about, with relatively small number of lines of code that need to be changed, addressing 70+% of the vulnerabilities in some of the case studies that have been looked at. Tremendous amount of promise, but also we need to do a lot of investigation about how this can be really used. Can we really, in industrial grade corpuses of software, get the benefits that the more limited studies seem to hint at? And particularly with things like the scalable compartmentalization, has been talked about throughout the session. We've got a big question about, if you are able to do much more compartmentalization than you can do today, what would you do with it? Is that really going to be a usable technology to put into people's hands? And really, what we're doing with Morello is putting out a highly capable system to allow people to explore what they would do given these technologies, to allow attackers to then say, can we find easy ways of breaking what we think are secured systems because they're using this technology? So again, we have to be sure that we don't just apply a sticking plaster to the problem, but that what we're putting out here has longevity. And the idea really about Morello is it's a prototype system to allow the experimentation that we need to get feedback from, to take this forward. And I keep stressing this prototype nature. What we put out there is it's actually bigger, it's got more functionality than we think would be deployed in a commercial system, because we want to try different ways of doing things and make choices between two different ways that the Cherry concepts could be used to be able to justify how to go forward. What does success look like if this program works out, and all of the work that all of the various partners that John talked about, and yourselves, if you access this technology through the Technology Access Program? What success really looks like is that people will find compelling uses of this technology in addressing security challenges, such that we're then able to really make the case that this should be a mainstream part of processor architecture. And I'm very clear here that we want that would be an enabler to see this in ARM's processors going forward, but we're not trying to monopolize this technology by any means. We'd be more than happy if this technology appears in x86 architecture systems, in RISC-V, in any of the processor architectures that exist, because actually that will mean that this is a technology that people can count on and be using wherever, and it just so happens that ARM's implementations have got it as well. And that's a very important part, that the fundamentals of the technology here are not being patented and any architecture is able to use it. This is not an attempt by ARM to monopolize this technology. So what have we produced? Some of the earlier talks have talked about this, and the website at the top there, arm.com/Morello, has links to all of this material. We have this prototype architecture. We have a software model of the Morello platform. We've got a form of the operating system out there. We've got tool chains. We've got a partner forum, an FAQ to allow people to interact with it, technical reference manual for the board, as well as this test chip and board that is now just about reaching the point at which we're making it available to the many participants in the Digital Security by Design program. What is on this board? The basic principle behind it is a highly capable board, capable to be used for both client and server type systems. So this is slightly unusual as much as we haven't targeted any particular market. We built prototype processors with this new instruction set architecture in it that are actually based on the processor cores, the Neoverse N1 cores that we have shipping and used in things like the Amazon Graviton G2 processors. They don't have this technology, but we took that as the starting point, and these are highly capable out-of-order processors. We put 4 of these down and enhanced it with this Morello capability, or adding in all of the Cherry technology that Robert has talked about before. And then as part of that, put that throughout the system. The board is being provided with 16 gigabytes of memory. That's expandable up to 32 gigabytes. It's got a PCI interface. It's fully compliant with the SBSA, which is a standard that we've been progressing in order to make it much easier to run software out of the box on these sort of systems. And just a couple of pictures of the demonstrator board. If we were live, we'd be actually showing you this running, but we'll have to make do with some pictures. It's all very well having hardware available, but hardware on its own isn't really what we need. We need hardware and software. And as Robert talked about, Cambridge has done a tremendously good job of doing a port of FreeBSD to make full use of capabilities throughout its technology. But we're also providing a whole bunch of software work streams as part of this program. And at this point, we've got things like Linux up and running. We've got full development environments and tool chains there as well. And we'll be continuing to update that. We started releasing this software in October 2020 to work on our software model that anyone can go and download. And now we've got the SoC up and running in people's hands. We're going to be expanding to bring in more of the application of Morello into the Linux kernel, and specifically supporting and enforcing capabilities at the kernel user boundary, and developing a GCC-based toolchain in addition to the initial LLVM-based toolchain. The range of software available, Robert talked about how we've got that very much capability focused, Cherry BSD. We've also got Android and Linux ported to this platform. UEFI and ARM's trusted firmware also all runs on it. So this is a really very capable board, capable system. It's got a decent graphics processor, so you're able to run graphics-oriented workloads as well as text-oriented ones. It can, as I say, be very much used for both servers and for server type applications and for client type applications, and the range of different partners really show that we believe this board can be used in many different places. And what we're really looking for from this is, having put forward this open, this initial software for people to make use on, is that many of our partners will be collaborating and porting more software and making it available for this platform to allow us to essentially bootstrap around this new technology. And really the question is, with doing this, what feedback are we looking to get? Really, we need to understand the performance questions around a wide range of different usage models, because it's all very well putting out these different usage models, but this is a foundational technology, and we need to understand which ones are going to be performant, which ones aren't, allow us to refine the superset architecture that we've created, and from that make decisions about which features really make sense for a commercially deployed architecture. We need to have compelling examples of why capabilities are useful. I've talked quite a lot, and Robert talked a lot about the scalable compartmentalization. How will people really use this to improve their security? Does that really provide the benefits that we think on paper that it should? Have we got some people actually faced with software that's been ported to these sort of platforms? Can they actually find ways of breaking the compartmentalization that has been created, and actually work around all of the benefits that we're claiming about? So we need to have some red teams going after us. We need to understand how the different languages and runtimes can really make use of capabilities. Matt talked a lot about C and C++, but we've got a lot more languages that run on top of this, JavaScript, Java, Rust, and so on. We need to understand better how the compartmentalization can be used. We need to understand the performance questions. And if this all works out the way that we think it will, this becomes a showcase to encourage other architectures to adopt capabilities, because really making use of that fine-grained compartmentalization, you want to be able to use that on any platform you're running on. So as I say, we're very keen to see this technology, assuming that it provides the benefits that we think it will, being used actually by many architectures. We've gained experiences of building an SoC around this processor architecture. It does have tentacles that go out into an awful lot of the system. We've made quite a lot of that available for other people to make use of, because the whole thing has been a learning experience. And by having that experience published, again, we are helping take forward this technology so that it can be widely used around the world. And at the end of the day, what we're hoping we get out of this is an architectural approach with formally proven security properties. Part of the work that's lying behind this program is a bunch of formal methods and formal proofs of the security properties going on. And from this, we will learn what to put into the future ARM architecture to give the digital security by design going forward. So the next steps, really, this is an opportunity for you to experiment with a Morello board. The technology access program that this event is all about is about giving you access, or getting you access to these boards if you wanted. We invite you to engage and contribute and be part of this program going forward, and just to help us understand whether this technology is worth genuinely deploying. We think it is, but this really is, if you think about it, almost an advanced beta test of this concept to see that this is really worth putting out into the world's architectures. And Katie will be talking about how you'll be able to get access later in this session.
Thank you very much, Richard. I'd like to now invite Professor Watson back on camera, and to invite George Papadakis, Senior Innovation Lead at Digital Security by Design from UKRI, to a short Q&A session before we start with the panel.
Thank you, Dana. We already have some questions that have come in. Some of those have been answered, but those that we can answer. So let's have this one now from Ian Crawford. He's asking, can Cherry be retrofitted to existing software systems, or does it need to be included only in new implementations? I guess that's a question for Robert, most likely.
Yes, certainly give it a cut. Maybe Rich will have some opinions too. But certainly our experience with this idea has expanded as a result of the collaboration with Arm and their customers. In general, Cherry is intended to be incrementally adoptable in software. So yes, you have to have a chip that implements it. Once the chip is present, then you have some choices about how you deploy Cherry, both in terms of how you use it and in what software you use it. We have generally recommended an incremental deployment strategy that consists of introducing operating system support early. When you introduce operating system support, there are then different paths you can take depending on what you want software to run. As with the 32-bit, 64-bit transition, I think it is reasonable to assume that non-Cherry aware software will run for the foreseeable future. That software will not get the benefits of Cherry, your existing program binaries, but also it can exist within an ecosystem, in some sense be protected from the world by the Cherry extensions elsewhere. On the memory safety side, essentially we have a new variant of C and C++. It is very similar to current C and C++, hence the 0.026 lines of code change for a very large software corpus, but it does require these modest changes. Those modest changes are generally hygiene changes. There are changes that will be acceptable in most cases to upstream source code repositories, vendors, open source communities, and we have upstreamed many of those changes. To perform software compartmentalization is a more disruptive change. Those sorts of changes do exist in some software already. If you look at, for example, the mobile phone vendors' operating systems, they often use sandboxing fairly heavily within web browsers, sometimes for plugins and so on. Those were disruptive changes on current architectures. That's not less true in Cherry. One of the challenges there is that maintaining both compartmentalized and uncompartmentalized versions of the same software could be more costly. We don't really understand that cost yet, but if it imposes structural changes, some of them will work on both, but testing and evaluation and so on is something you need to think carefully about. Obviously, we view a future world in which you're gradually moving towards extensive Cherry use, yet to be seen if that will be fulfilled. But we've worked very hard to provide a rich software ecosystem with debuggers and tracing tools and so on to help with that process. Happy to talk with people offline if they have questions about our experiences.
Thank you, Robert. There's another question from John Dalman. He's asking, Richard, how much does the Morello board cost?
Well, we're not actually making this a commercially available board. As I talked about a little bit before, this is a prototype architecture, and actually we're not providing backwards compatibility to this architecture. This is very much a prototype to allow people to experiment. And so we don't want it to be incredibly widely available. We want people to be able to participate. So the way this program's been put together through the Digital Security by Design and through what's going on being talked about as part of this Digital Catapult event is that we're providing access to the technology for people to be able to participate with the boards rather than making them widely available as a commercial offering. What that then allows us to do is actually have a bit of a partnership with the people who are using the boards to understand what's going on, and then once we get all the feedback and we say this is a great technology going forward, it will become part of a mainstream technology from ARM, at which point it will become commercially available.
That's great. Thank you, Richard. And last question, Robert, you did cover the retrofitting aspects. Christopher Williams is asking a question. In addition to the retrofit, he's asking whether changes in the C and C++ standards are needed to take full advantage of Cherry, basically.
It's an interesting question. I mean, we've tried to work wherever possible within the existing standards. I mean, one way to think about what we've done is that we've taken undefined or implementation defined parts of C and C++ and defined some new behaviors such as trapping when a buffer is overflowed. But we do require some changes in how pointers are used. The syntax of language remains the same, but for example, you can't fit a full pointer inside your regular sized integer anymore. You have to use int pointer t, and this sometimes causes some source code change. We have a Cherry C and C++ programmer's guide available on our website, which I think does a pretty good job of exploring these issues. We plan to do an updated version of that later this year based on new experience gained. We've also done some work around, for example, compiler-based static checking to look for potential issues. About half the issues we find importing source code to Cherry are picked up by at compile time by the compiler, but then there's a set of dynamic issues that can arise around memory alignment or pointer misuse. These tend to be picked up by various sanitizers or through dynamic testing. This is a topic I have to talk to people about in more detail if they find that useful.
Yep. If I could just come in a little bit on that, one of the things we've learned from this overall program is that people don't really follow the rules of C. There's really quite a lot of de facto programming in C, and actually the way Cherry's been designed is to fit in with that de facto usage rather than the letter of the law as much as is possible. And there's been some really great papers which are on Robert's on the Cambridge University site that Robert talked about that actually talk about, you know, what is the de facto expectations of C, not just what the letter of the language says, because it is quite astonishing what we've learned from all of that.
Thank you both. Final question from right. There are more questions coming in, but I'll have to draw the line here. So I'll pick one from Tommy P. Christopher has already asked one. Has there been any research on how much modification or effort is needed to get Java or JavaScript working with capabilities?
Yeah, maybe I could take this one as well. To some extent, with respect to JavaScript, we have the WebKit JSC JavaScript core runtime up and running on Morello, including a just-in-time compiler. This was collaborative work with ARM. It works very well. We don't have, in terms of functionality, we think improved security as a result of the resilience. We're looking to do a structured evaluation of security change and also performance impact over the next 6 months, and can hopefully report back more on that. There is an OpenJDK adaptation taking place as part of the University of Manchester, Manchester University contribution to the Soteria project, which is an Innovate-funded project. Probably too soon to talk about results from them, I expect, but I think this is one of the questions we really hope to engage with in the first year of this program is what happens with these managed language runtimes? How do they perform? How easy is it to adapt them? And do we gain security benefit for them as well? I think we have good reason to think we would, since vulnerabilities in language runtimes are quite a big thing currently. Often the language runtimes are written in C and C++. They suffer from all these exciting problems, but much is to be learned there still.
And just to be slightly clear there, that's essentially modifications to get the runtimes running. You're not going to have to change your Java or your JavaScript programs at all to make use of this. This is absolutely underneath the hood. It's below the language level stuff.
Thank you very much, both. I'd like to bring this Q&A to an end and hand back to Dana at this point. Thank you all.
Thank you to the speakers and for the audience for the questions, and for George for the facilitation. Now we're going to introduce the panel. So I'd like to ask George if you can come back on screen and introduce the panelists.
Thank you, Dana. Indeed, for our next session, I'd like to invite our esteemed experts for a panel discussion. We have Richard and John already spoken, but I'd like also to invite Professor Madeleine Carr from University College London, Professor of Global Politics and Cybersecurity, and also Paul Waller, Head of Research at the National Cybersecurity Center. I think, Dana, in the interest of time, we might want to make a start whilst Madeleine resolves connectivity and other issues.
Yes, I agree. Thank you.
So thank you very much. We're going to have a Q&A discussion with our panel and our experts, at the back end of which we will endeavor to get questions from the audience as well, time permitting. We are slightly behind time. When you post your questions from the audience, please make them clear and succinct. That will be much appreciated. Right, so we heard about this new technology, Morello, Cherry, digital security by design. One may ask Richard, what exactly is the proposition here? So John mentioned about vulnerabilities are in essence mistakes. So is this technology correcting mistakes? Is it putting an end to mistakes? What exactly is it doing?
Interesting question. I mean, I think Matt touched on the fact that software has mistakes in it. There are, billions and billions of lines of code out there, and a huge number of things essentially is assumed that, oh, when I go and talk to this array in memory, I will only my access into it will be within the bounds that are given to me, and or the bounds of the buffer rather, and I haven't got any problems. And people haven't thought about what happens if the pointer coming in is out of range. And these sort of mistakes exist throughout software. It's actually really quite remarkable when you start digging into it and use technologies that can look for these things, just how common it is that that essentially either memory is used after it's been freed up, or that accesses to memory go out of range, and all of those sort of things. And so turning around and saying, well, people should write software perfectly is just naive. In reality, there is so much software being written at any moment in time. There's always going to be mistakes. Human beings are inherently prone to creating errors, and we can't just turn around and say, it's your fault, you shouldn't do that. We need at the hardware level to be saying, well, if we assume there are going to be mistakes, how can we find them in the field, and how can we prevent them being exploited? Because what you have is this mistake is a vulnerability in the software, then some clever hacker finds a way to stimulate that so that they're then able to exploit that and gain access, gain a step towards getting access to the computer. For example, by going out of range on the stack, they're able to overwrite something that then when you do a return, you're able to select where you branch to. So yes, we're dealing with a world of mistakes, but we're dealing with the fact that across billions of lines of code, there will always be mistakes. And what hardware needs to do is be resilient in the face of that. And so the memory safety that you get out of Morello, out of the Cherry technology, is a key part of that. The other key part is that with the compartmentalization, the ability to fine-grain compartmentalization that we believe can be built from this technology, that when people are able to break out, to exploit a mistake like that, the amount of damage they can do is reduced. So that means that one little exploit doesn't give you access to everything that's going on. It gives you access to a much smaller thing. And that, I think Robert talked about, is raising the workload that has to be done by the attackers in order to be able to achieve any valuable endpoint. But this really is a recognition of the fact that the world cannot have perfect software, simply because there's just so much of it written, and people are inherently the push for time, the push for resources, they're reusing old software in slightly inappropriate ways. All sorts of reasons like that means these mistakes will always actually exist.
Sure. Thank you, Richard. I'd like to turn to Paul and ask about who is this technology for, and why would people want to use this technology?
So I think, excuse me, I think there's a lot of potential uses for it, and its strength is the sort of ubiquity of it. So the idea is obviously to make sure that in time, Cherry technology and indeed Morello technology becomes the right way to do things, and it becomes more usable the more widely available it is. But I think initially, people interested in using it will be those who most benefit from the reduction in harm that Richard was talking about. So containing mistakes and vulnerabilities, making them more expensive or more difficult to get the same level of damage from. There's a lot of industries where there's interest in this now in order to improve the resilience of devices. So things like automotive, anything safety critical or medical, a lot of the industrial stuff. Where there's interest now, but also more interest for future innovations. A lot of the things we're looking at doing more of along the lines of artificial intelligence, machine learning, connected places, and more wide-scale access to big data resources requires a huge amount of confidence in the security of the platforms that we use. And it's up to us as a society to engineer that confidence and make sure that it's there and that people can rely on it. And we need to do that right from the ground up, and that's why I'm really pleased that an initiative like this one is able to start from the architectural level and empower that confidence all the way through the software stack.
Thank you, Paul. On the back of that, if I may turn to John now. John, what are some of the use cases that you are seeing in the program through the projects that you fund?
Yeah, it's interesting because obviously I think everybody's got the idea that we're fairly early on in the investigations and the prototyping, but one of the things we did in the program quite early on, as I mentioned in my talk, was expose this through the software model that Richard spoke about to a number of SME companies. And as a group, obviously it was new technology. some of the questions we've had in the Q&A, can it be retrofit? Can I put it on a PCI bus? Missed the point that it's actually fundamental in the CPU to what's being changed here. And the projects, I think, ranged from a very thankful realization that they can actually catch third-party code vulnerabilities. So the idea that they just recompiled and actually now got a compiler flag, a compiler warning, well, I think it was a failure rather than a warning, that said basically this library that you're using has got a vulnerability in it. And they just went, oh, and that was just wide open. We had a couple of others that actually did manage to go into what does it mean to their compartmentalization. And they were doing some identity libraries for proving identity. And obviously the key thing there is to keep all the different parts of the code separate to each other. And they were very happy in the way that they could, build these distributed applications on a single machine. So really, the sectors that are going to go for this are the ones that care about security, care about the resilience of their solutions or the safety of their solutions, where in time it'll hopefully become the de facto way of always building more secure technology solutions. So I think that's where we're at, is that who's it for? When it's for everybody who ever thinks they might use or build something on top of a computer, who will get there first? It's the ones that worry today about the resilience of their code, etc.
Thank you, John. Good to see you, Madeline. I hope we can hear you as well. Can we have a quick check?
Yes, sorry, George. I don't know what happened there.
Excellent. So Madeline, thanks for joining. In one respect, this technology can be considered arguably emerging technology, right? A new technology. And since it's not yet mainstream, how would businesses consider such an opportunity since it doesn't exist yet?
Yeah, well, that's a really good question. And there's a lot of work that's been done on how new technologies or emerging technologies are incorporated into the commercial sector. And there is often this kind of period that we're in now where we see a huge investment from government and a significant investment from the private sector to try and build this understanding of a business case or a commercial case for emerging technologies. I mean, this was very much what happened with the internet. If we think back, which was also funded significantly by DARPA, that the US government had put so much resource into that, really struggled to get the business sector to see that there was an opportunity for commercializing that technology, frankly, until the PC market it exploded. And then suddenly the understanding that networking technology was absolutely fundamental to the potential of the future of a digital economy became clear. So these are these things we call, in my field, we call these the reverse salient. This is this point, this bottleneck, or this point which is preventing emerging technologies being taken up. And really these security problems that have been so carefully and clearly explained today by the others are what is standing in the way of our future digital economy of technologies like, well, full implementation of the Internet of Things or safety critical systems like connected autonomous vehicles. We have to crack that cybersecurity nut. And for any business leader who works in the future of secure solutions, I mean, this is sort of maybe not the ground floor, because we've had 10 years of work on this, but it's certainly one of the lower floors, the early opportunities to be involved in something that could be really transformative.
Thank you, Madeline. I'd like to turn to Richard again, if I may. We've heard about the promises, if you like, quotes unquote, or the potential of this foundational technology. And one would think, what about performance? Doesn't security slow things down, Richard?
Well, I think you've got to recognize that actually people currently do an awful lot of things for security already. So they're already actually paying quite a lot of performance cost. And so actually, if we can simplify some of that and make it easier to do, it can end up speeding things up. To take the compartmentalization story, a little bit again as being one of the big areas of research that I think we're going to get out of this program. We know that people currently use essentially a process-based compartmentalization. That is, you take your web browser or your mail tool that Robert was talking about and split up what it's doing into lots of different processes, and essentially use a lot of interprocessor calls to go between these different processes. And those add overhead. They put pressure on things like the TLBs. There's a lot of page table manipulation got to done. There's a lot of actual software overhead going on in order to do that compartmentalization. The promise of the compartmentalization that you can do through the Cherry technology is that you end up with being able to do it cheaper. So actually you could get the same level of security as we get today at a lower cost, lower performance cost. So actually things go faster, or you can use it to have more security at the same performance cost. So actually, yes, there is a cost to security compared with leaving things wide open, in the same way as when I go out of the door or come back home in the evening, I have to put the key in the door rather than walking straight in. But that's a security cost I'm prepared to pay, because performance cost in my life that it takes me time to get through the door, because I don't want people walking in and out of the door. It's just part and parcel of it. And what we're trying to do here is actually make it actually easier to use this, and that will actually, in some cases, improve performance. But equally, other places, you may find security is paramount and they're prepared to pay the performance cost. So I think there really is a range of different ways this can be used. It might, consistent with what Madeline was talking about, there can be situations where, frankly, if we don't get the security right, people will simply not use the technology, and then the performance cost is entirely acceptable. In other places, we can effectively give similar or slightly better security than we get today at a lower performance cost than people are currently paying. And also we also know that people do all sorts of weird things under the hood in an ad hoc way to provide security, that again, this will systematize and people will find it perhaps more productive, and the cost will be pretty small. Robert talked about what the general performance cost is, for substituting all of the pointers with capabilities. That sort of 0 to 5% was in his slides. But you don't need to sort of take that away and say it's an absolute given. There's a lot more experimentation. That's part of the reason we want this board to be available, is so that people can really tell us, does this work compared with what I would be doing otherwise?
Yep. Thank you, Richard. Matt mentioned earlier about memory safe languages like C# or Rust. I'd like to ask Paul, where does this technology stand against that promise that we're going to solve our security problems of this world through memory safe languages?
Well, I think there's a couple of different ways of thinking about it, and Rich has just done a great job of explaining the tools that Cherry and capabilities give us hardware options to provide some of those memory safety options at a very high level of performance, and perhaps even better alternatives to what we're currently doing, and giving people the option and the sliding scale of, do you want more security or do you want the same security as before, but with a lower performance cost? And the same kind of things come up with choosing languages and balancing a choice of which language to use versus whether you want the hardware protections or the software protections, or indeed both. Cherry seems to provide extra options in terms of compartmenting code, and that contributes to resilience as well as safety from security bugs. Makes things easier to maintain and to analyze. There's a lot to be said for doing that. Also, I think has been discussed earlier, there's a much lower overhead cost in adopting Cherry in legacy code than there is in completely rewriting it in a new language. And there's a huge amount of legacy code out there, which, for good or ill, we are going to keep using and we're going to keep seeing across our society in places where we really need to care about its resilience and security. And so in some cases, the right thing to do is going to be to go straight in with new hardware. Of course, the safe languages have a place, and I think there's a lot to be learned, as Richard's been saying, about the best ways to use these tools. And the panel, I don't want to put words in their mouths, but I think we are convinced this is a force for good, and there's a huge number of benefits that we are already aware of but we look forward to researchers and developers uncovering more as new products take shape and reach the market.
I would just quickly, if I can just quickly come in, having been, working in for ARM actually for the best part of 25 years, the number of times I've been told, oh, you don't need to worry about this. The new language will come along and you never have to worry about these problems. I've heard that for about 25 years and it doesn't happen. People carry on using the existing skills, the existing language, the existing code, and they all have a place. It's not, we're going to have better languages and we're going to have better hardware, and you need to have both in our view.
Thank you, Paul.
Really
Thank you,
agree.
Richard. I'd like now to come closer to Madeleine's expertise in a way, and to ask Madeleine, what's the role of policy in motivating discussions about such foundational technology?
Yeah, I mean, that's always been a role of governments, frankly, is where we see a kind of market failure, which was described by John in the beginning, that the governments do have to step in and they have to create some kind of initiatives, very much like that case of the internet or email was another one where, really in the 80s, the US government tried very hard to get the US postal system to commercialize email, because they saw that as intrinsically linked to the delivery of physical mail. But the US Postal Service didn't see that opportunity, and the government had to sort of continue to try and find an opportunity to commercialize that. It's a very, there's a very long legacy of governments taking that role, either to try and stimulate it, by demonstrating a business case, or by other mechanisms. And now we're seeing really like quite a change in the digital economy, where governments in places like the UK, the US, Australia, the EU are beginning to take this more proactive regulatory approach, where they're really defining where liability for breaches lie in the business sector. So both, specifically for senior business leaders and for board members, but also for organizations themselves. So we're seeing this shift from this kind of do your best to now much more of a regulatory heavy hand that imposes fines. And then we're also seeing this shift from individuals that are increasingly sensitive to the misuse of data and to safety issues that arise from engaging with insecure technologies. So where in the past, people really just took that for granted and kind of learned to live with it. We're seeing that change both from a consumer perspective and from a business, from a government sector. And so that makes this very much a business issue then, because as I said, the future of any digital economy will rely on a willingness and an ability to implement emerging technologies. And some of those, just the security issues and the safety critical issues will be prohibitive. So for those, business leaders who are thinking to not just the cybersecurity problems that we encounter now, but what could we open up in the future if we thought more creatively and more broadly about cybersecurity? The kind of the sky's the limit, really.
Thank you, Madeleine. The other point, Paul, is for those technology businesses that are too busy developing their solutions at the moment, this technology might seem far out in terms of their future roadmaps, right? So what are some of the standing barriers for them, for those technology businesses to see this opportunity and understand this opportunity now?
Well, it might be far off, but it is coming, and part of what we're doing in the Digital Security by Design Challenge and the surrounding community is kind of preparing the ground for it. There's a range of activities being undertaken at the hardware level, as we've described, but also looking at the tool chain and the compilers, and more of these technologies will be coming online. And so it kind of depends where in the technology stack these businesses sit. But in terms of low-level developers, the technology primitives are there now and should be part of people's research horizon scanning activity. we're looking forward to getting the development programs underway to investigate uses of these technologies. There will be some where it's not quite time yet, but actually proactive, forward-looking businesses who are looking to exploit, as Madeline said, emerging technologies and new types of business will need to realize that if they don't have customer confidence in their technologies, that things are not getting deployed. As regulations do get more heavy-handed, or more transparency is required in which security mechanisms are implemented and how they're supported, people are going to need to be able to show they're doing the right thing and using the most resilient technologies available. And so they need to be considering all of the options, including this.
Thank you, Paul. And extending that to John. So John, from your viewpoint, what are some of the elements of success, if you like, for the program Digital Security by Design? And what are you already doing about those for this technology to succeed?
Yeah, so I'd start by recapping the vision of the program. It's sort of twofold: to overcome the market failure, this problem of how do fundamental technology changes of this start into the supply chain, because hardware, software is an industry, because it takes many years to get a new hardware architectural design out, but I can write a new piece of software next week. How do you align those two things in terms of getting it through? So I think success for the program is that the answer, does this hardware concept work, is probably the main success factor. Can there be enough evidence to show that it's both secure, but it's also, we've heard about the performance questions, the opportunity questions, are those answerable within the next year or so? And that I think is the key part of this. When we look out to what success that means, then really that's where what Madeline was describing, not only in the application sectors today that we need security and resilience, but if people, the problem at the moment is there's so much bad press around security this, security leak that, ransomware that. At what point do people actually shy away from using digital technologies? That I think that would be the biggest opportunity we have, is that doesn't happen. Okay, we can actually go out and know that our data is private, know that our bank account's safe, know that our computer's not going to be locked up and I can't open the doors anymore because the key doesn't work. So I think that's really where the success is. But the program itself, as you've heard in the last hour or so, it's around getting the technology out there, understood, making sure the businesses understand the opportunities they have to actually make security a differentiating feature in the delivery of their products. Today we hear, hardware agnostic, and security, really, cybersecurity is a problem for the user of the system, not the developer of the system. Okay, let's try to move that needle towards making sure that the solutions are by design and configured by default, so that the user still has their protections at the point of use, but they're not having to run around on a day's notice when a vulnerability pops up. The cost of that just must be astronomical for businesses. One, to have them on staff. Two, oh dear, we're going to have to turn off all our computers because one of them got infected. That kind of disruption to productivity. Those are the challenges that I think the program hopefully will open the doors to resolving.
Thank you, John. Madeline, when we think about senior executives, right, board level, what would it take for them to appreciate this opportunity presented to them?
I mean, I think business leaders are always looking for a risk to exploit. The idea that, as John said, this kind of business as usual supply chain is not something that every sector or every industry could be even contemplating disrupting. This is a major issue. At the same time, it's a huge risk to be exploited, because what kind of business as usual supply chains absolutely must function, and where are the opportunities to develop solutions for those supply chains so that it can be ensured that they do. Because at the moment, there are very few supply chains, if any, really, that aren't vulnerable to these kind of these kind of threats and disruptions. So in my mind, it's those kind of business leaders that are looking at cybersecurity as a risk that some businesses cannot tolerate, and therefore, what are the opportunities for technology like this to develop a solution to address those kind of issues that are intolerable. And this is very much in this context of business leaders being increasingly liable, personally and professionally liable. So in so many sectors now, senior business leaders are looking to understand how can they shift that liability. Insurance is becoming increasingly difficult to write because it's so difficult to quantify these threats and vulnerabilities that insurance companies really are becoming increasingly reluctant to write policies on this. And yet senior business leaders are becoming increasingly liable. So there's a huge market out there really to address those insecurities of senior business leaders by developing more secure solutions. And as we've heard today, after 45 or 50 years of effort in cybersecurity, we are where we are. And perhaps, in large part, the effort has gone on software solutions. And this is an area that we really haven't developed anywhere near as far as we need to.
That's great. Thank you, Madeleine. John, I'd like to turn to you at this point. Earlier, Robert alluded to the fact that these technologies are attracting interest from overseas organizations, not least DARPA's interest as well. Would you like to take us through some of that interest that's happening overseas?
Yeah, I think there's a couple of things to say on the scope of the program and the scope of the technology. The technology is obviously global. Okay, we are talking around basically changing the digital world, and the world being the big thing we all live on. Yeah, the program DSDB is obviously UK focused in terms of the aspects and the partners it's working from. We work with the UK registered businesses, etc. But that doesn't mean that we don't have global interest, whether that's through Arms Partnership. They obviously have partners throughout the world that are looking and monitoring this, so there's clearly international there. And then on the research side, we have I think DARPA's actually mentioned that they are looking at this technology as well and reaching out to their partners in terms of providing access to the technology. So I think it really depends on how global you think it is. Obviously there is a limited number of boards, so we're not doing this everywhere. But clearly, the importance and the relevance of the international part of this is key to its global success.
Yeah, if I can just echo that. I mean, the original announcement of this did talk about, in particular, Microsoft and Google being significant backers to the program, and they are putting in a lot of their own research efforts around these boards because, frankly, we need some of these big ecosystems, such as Android and so on, making use of this technology to really to reach that vision of ubiquity that we've been talking about throughout this session. So there are definitely quite a lot of international partners through ARMS connections as part of this. This particular access program we're talking about today is very much UK focused.
Thank you, John. Thank you, Richard. Starting to bring in some of the elements from questions from the audience. There's a question about whether Morello will be exploring low power requirements, Richard.
Yeah, I mean, we've actually got, for those of you who are familiar with the ARM architecture and the products that we provide, we have multiple profiles. We have the A profile, which this thing's based around, which is really aimed at perhaps bigger compute systems, and we have an M profile. We have a prototype of an M profile version of this in development. It's got slightly different constraints because they tend to be 32-bit architectures, and so the way that you encode a capability is a bit different. but we're very much looking at this. We do see this as being important for the Internet of Things in the sort of sensors and in all of these little embedded devices, as well as in the big computers. And so absolutely, we're looking at this in that context. And I know that Cambridge have been involved also with other architectures on this. I think they've done some stuff with RISC-V in this area as well. So yeah, absolutely. This is not. You shouldn't leave this session with a feeling that this is a big iron technology only. This very much scales down to low power systems. The research platform that we've created in this situation is there for larger systems we talked about, but it doesn't stop the learnings from it being applicable all the way down to the smallest servers, smallest sensors and actuators.
That's great. Thank you, Richard. I'm mindful that we are nearing the end of this panel discussion. We've taken questions from the floor. Just as we wrap up, I'd like to have from you, from your side, in a few sentences, what do we want people to think about this technology? What would be the key message from today to take away? Let's start with Madeleine first, perhaps.
Yeah, thanks. So yes, for me, the key messages would be that we're at, I see this as an incredibly exciting point. This is very much the emergence of potentially transformative technology. And for business leaders who, who have the kind of vision and foresight to understand how that will impact in the future and what kind of potential that opens up for a digital economy, for transforming society. There's this incredible ecosystem here with this huge investment from government in the research community in the UK, from really significant support from the private sector, from ARM, and this incredible opportunity to be involved in something that's happening now. And for me, it's an exciting opportunity.
Thank you, Madeleine. What would be your message, Paul?
Well, I would echo that. I think there's an opportunity. There's been a lot of investigative research into the technology and development. So kudos to the team at Cambridge and all of the people that supported that work. Also a huge amount of work by ARM and other tech companies in kind of preparing the ground. There's clearly a lot of confidence that there's some really important use cases for this, but also that there's further uses and further opportunities that maybe more than we can imagine. Richard started to talk about different ways of reducing harm and also of interesting ways of balancing performance and security. And I suspect we really don't know how deep that seam can be mined for interesting operations and new ways of doing things. So what I'm really keen to see from this program is people exploring what can really be done with the technology. We know it's good. But what are the limits? What are the really interesting applications that we don't even know about yet? And I really look forward to seeing those from the Access program and from innovative people exploring what can be done with something really cool that some of our finest minds have collaborated to produce.
That's great. Thank you, Paul. What about you, Richard?
Kind of much the same. I mean, I think this is a fantastic opportunity. We're really proud to be involved in the program. We're really fascinated about how this technology will be used. We've put a lot of work into creating these boards. The saddest thing will be if they don't get used and everyone goes, "Oh, that's rather interesting. It's a nice ornament on the shelf." We want to see these boards widely used, and this event is all about describing a technology access program, and the real takeaway I want from people is use this opportunity to participate, to work with ARM, to advance security, because as Madeleine talked about, almost the limits of what we will do with computing will be limited by the degree to which people trust the systems they work on, and security is a huge part of how society will change because of computing. I think this is a step towards making computing safer, more trustworthy, and really important that people take the opportunity to learn more and help us understand it better.
last but not least, John, what would be your few words for the takeaway?
Yeah, I think we're at the businesses are at a decision point. They, we've heard the technology, you've heard the belief of the technologists that there's something good here, and now you need to make a decision. Are you going to sit and wait, and it might show up again in your inbox as something, or your product was hacked, or you're going to start investigating what it means to your products and services so you can be one ahead of the people that are suffering in the new world.
Thank you, John. I'd like to bring this panel session to an end, and thank you very much for this excellent discussion. Thank you all, and thanks for the audience for their questions as well. I'd like to hand back to Dana at this point.
Thank you to this insightful discussion, to all the panelists, and to our chair. I'd like to now invite Katie Ho, our Head of Innovation at Digital Catapult, to present on getting involved in the Digital Security by Design Access Program.
Thank you very much, Dana. So I'm going to talk a bit about the Technology Access Program in particular, and the benefits that you can get from it, and also how it's structured and how you can apply to be part of it as well. So as you've heard today, the Technology Access Program is really your opportunity to get involved, to explore, to experiment with this new technology and be part of the early ecosystem around this technology as well. So it's both an awareness program where we'll be running a lot of webinars like this, technical deep dives, and also events across the UK, and also an experimentation program where we work very closely with you collaboratively to look at what are some of the use cases and innovative applications, and also what are some of your feedback and technical validation for what has been developed as well. So you will have this rare opportunity to explore this before the rest of the ecosystem in the UK. So your findings and feedback, of course, is very important. It will really influence how we take this forward in the future. And for us, it's really important that we open this access as widely as possible in the UK. And with this in mind, we've developed 2 levels of participation for this program to take into account the different sizes of companies that might be interested, and also the amount of time and resources that you might be able to dedicate to this experimentation as well. So the way the program works is that there are 2 routes that you can get involved. So the first route is really focusing on startups, SMEs, smaller companies who really want to experiment with the technology. You would have a pretty good idea of some of the use cases and experiments that you want to run, and you will have the opportunity to work very closely with us through regular technical sessions, hands-on mentoring and development. And what we will ask for you is to give us regular feedback and also progress, and also show us what you've been up to on a very regular basis. So for this route, you will have board access for 6 months, extension if needed, and also grant funding of 15K. The second way for you to get involved is more of a light touch option. So this is suitable for larger organizations. They're not eligible for grant funding, but also for startups or SMEs who are just looking to play around a little bit and explore what you can do, not necessarily with any defined use cases or experimentation roadmap in mind, or if you're very resource constrained and you're not able to work with us as closely as the first route. And what we will expect from this is, of course, some final feedback at the end of the program. And you will be able to get the board for 6 to 12 months in the second route as well. So one thing to keep in mind is that for both of these options, you'll be part of this community and you'll get access to the relevant resources, expertise, and support from Digital Catapult as you go through the program. So what are some of the benefits that you get? So of course, you get early access to technology and expertise, not just from Digital Catapult, of course, from everyone you've heard from today, and the wider consortium for digital security by design as well. You'll be able to receive guidance and support along the way. If you want to pivot something you're doing, if you want to provide early feedback, we're there to engage with you every step of the way. And really is about this opportunity, as we heard today, to explore the impact for your organization, for your products, and for your capabilities. And the second group of benefits, of course, is a community of network. So really being part of this community, collaborate with not just, again, the Technology Access Program, but be able to speak to other projects that are funded through Digital Security by Design, and also universities, academia partners as well, and really contribute to some of the open source projects that are available as well. And of course, lastly, being an early adopter, looking at being very visible in your industry as innovating in cyber and digital security as well. So who should apply? So as mentioned, we want this to be as open as possible. So for this cohort, we're opening it to all types of businesses, from SMEs and mature companies that are seeking early access to this technology. We're not restricting to any particular industry for this first cohort. We know that for some industries, there might be some more relevant impact, early impact, but we really want to see some of the ideas that you have out there. So we're not going to restrict this to particular industries for this cohort. And of course, it's open to experienced software developers as well, and also companies with specific expertise that are relevant to this technology. So this information is also on our website, which I'll point you out to later. But as this is a prototype, there are some technical considerations, and what is available out there is still being developed. So those have been highlighted by Arm Cambridge earlier. But you can also find all this information on our website to understand what can you do at the moment, but also help you to look at what's the scope for your experiment. So how can you get involved? So at the moment, our open call is live as of today until the 6th of March. And what you need to do is to register your interest on our new website that's also launching today, dsdb.tech. On dsdb.tech, what you'll find is a source of knowledge of everything that's happened in digital security by design, and we'll be signposting to different partner content on that website as well. So what you need to do to be part of our first cohort is to register your interest to receive a full application form, which we will be emailed to you after you register your interest. On the application form, you'll then let us know whether you want to be part of the more involved 6-month grant funding route or the more light touch route where you get the board access only. So we do have a set of selection criteria for the program, which you can find in the FAQ document on the website, alongside some terms and conditions as well, which you just need to read through. The deadline for this open call is the 6th of March. So you would need to complete and also submit your application before the 6th of March to be part of our first cohort. And we do have a judging panel, expert judging panel that will assess the application and notify you afterwards. And if you're successful, Digital Catapult will get in touch with you with onboarding details, necessary agreements to be signed before you're formally onboarded through a event that we'll be holding by the end of April. So within this program, what we'll be doing is we will have 4 cohorts in the next 2 years that will be very closely working with us. If you're interested in the board only, there's a little bit more flexibility in how you can get involved there. But in terms of the tier 1 route, which is 15K of grant funding, more involved, more support from us, and also more collaboration on the feedback side, we will be running 4 cohorts. So very pleased to be launching our first cohort open call today, and please do go on the website to register your interest. So as I mentioned, the big part of this is also building the community and building awareness of the benefits of this technology. And also I want to allow you to exchange learnings with other cohort members throughout the year. So I just want to point you as well to some of the upcoming events that we'll be hosting around the UK. And this is hosted by both UKRI and also Digital Catapult. So we'll have 2 events upcoming at the end of February, both in Cambridge. And then we have, we'll be going to Glasgow, Newport and Belfast as well. So please do get involved, and please let your network know to get involved as well if you're interested, and find out more on our new website, dsdb.tech, and of course on different social media channels as well. But we're really interested now, really, really pleased to have all of you involved in this program, and looking forward to seeing what ideas you come up with and really working closely with you in the next 2 years to make this happen. So that's the end of my presentation, but I'm happy to take any questions around the program.
Thank you very much, Katie. I see that there's one question in the Q&A box. Is the grant de minimis?
Yes, I believe so.
While we wait for more questions, I'd like to ask about other opportunities to apply if companies are not feeling that they're able to apply to by 6th of March, what are the other opportunities that they'll have?
Yeah, of course. So we'll be running 4 cohorts in the next 2 years. So of course, if you miss this deadline, we'll be running another open call very soon after that for cohort 2. There's also options to apply for a board and board only. So if you don't want to commit to sending us feedback or looking at working closely with some of our technologists, there's also an option on DSDB.tech where you can apply to just get a board. But of course, what's really valuable about the Technology Access Program is that collaboration. So I would encourage you to apply for the Technology Access Program if you're able to dedicate some time to work with us and really access the full range of expertise that we have within the consortium.
Thank you, Katie. I just want to mention that we also have a frequently asked question part on the website, and we are happy to answer any questions that may come as well after this event. I see another question from the audience. Will there be a cohort for students and/or universities?
So we don't have a cohort currently planned for students, but universities are more than welcome to get in touch with us about participation on the program. And please do let us know. I'm happy to pick up this conversation after this webinar as well, to look at what are the requirements from the university in terms of the number of boards that you might require, and what are you thinking regarding the engagement process as well. So more than happy to have a chat, but very much open to academia to collaborate on this program.
Another question from the audience is, how large will each cohort be?
So at the moment, we are looking at each cohort to be around 10 companies, and this is for the tier 1. So that's the grant funding route. And the reason for setting that number is that we want to be able to really work closely with the companies and dedicate enough time and support for each company. But there is a much higher number available for tier 2, which is the board only. So of course, there is a limitation on the number of boards that we'll receive over 2 years, but our initial thinking is that the tier 1 route will be 10 companies per cohort, and for tier 2 we'll have more.
Thank you very much, Katie. I'd like to now to thank all the speakers, thank the panelists, and thank the teams that were involved in making this event happen at DC and with our partners and UKRI. So thank you very much for joining us today. And please see more links to other events, the website and the open call in the chat. Thank you very much.